the summer of 1959, Perini was awarded a contract for the construction of the substructure of 7 piers to support a bridge designed to span the Fraser River. A total of 612 piles were to be installed to varying depths between 150 and 200 feet. The design of these piers was unique, as the bearing piles were required to support an exceptionally high load of 50 tons per square foot, and the piles were to be inserted into pre-bored holes to an exceptional depth. Of these 7 piers, 3 were located in the river itself and 4 on the south shore. This design and method of construction was an engineering first on the American continent. The following diagrams illustrate the various stages in the piling operation. Here is a cross-section of the river showing the underlying strata. The contract drawing showed an estimated penetration of 1 foot into the glacial till, as shown here by pile number 1. Actual drilling experience, however, showed quite different situations. For example, pile number 2 is seated on a large boulder lying above the clay bed. In case number 3, the pile bored completely through a boulder before founding in the glacial till. Example number 4 indicates a pile which was required to be drilled completely through the glacial till layer. Pile number 5 is founded on the gravel on top of the till layer. In case number 6, after entering the glacial till, the pile encountered pockets of soft material, finally founding at the bottom of the till. Finally, diagram number 7, shown here in red, illustrates the average founding depth of 9 feet into the contract drawing glacial till. Drilling in soft material is undertaken by a rotary drill operating inside an outer casing. As the drill rotates, the outer casing is oscillated horizontally through a 22-degree plane. At the same time, the casing is alternately raised and lowered to assist penetration. As drilling proceeds, air and water is introduced into the boring between the drill and the outer casing, and a mixture of sand, silt, air, and water is forced up through the drill stem by means of an airlift. This operation is carried out with a standard Bonotto machine using a drag bit fitted with removable cutting bits. When hard ground is encountered, a clamshell grab bucket is substituted for the drill, and a mud solution is introduced into the casing to prevent blow-in of material and to provide additional lubrication. During the clamshell operation, the outer casing continues to oscillate. After placing the pipe pile, the lower section is filled with dry concrete and hammered with an internal drop hammer. When the pile has been driven to the required resistance, it is filled with concrete. Each of the 612 piles were driven to depths varying between 150 and 200 feet, and each pile required an average of 20 cubic yards of concrete. The next stage in the operation is the introduction of clay grout, which fills the space between the pipe pile and the outer casing. The grout is designed to prevent overloading by friction due to settlement of ground, and also provides additional lubrication during withdrawal of the outer casing. Finally, the outer casing is withdrawn, leaving the concrete-filled pile in place, surrounded by the grout. This operation is carried out by means of a Bonotto extractor, which, in addition to raising the casing vertically, also oscillates it in the same manner as it was inserted during excavation. In the film that follows will be seen the actual equipment used on this project in the same sequence of operations as illustrated in the diagrams you have just seen. This is a view of the pile installation on one of the river piers. This Bonotto machine is designed and manufactured in France. It's hydraulically operated and performs the simultaneous functions of sinking the casing and excavating from within. The sinking of the casing is achieved by oscillating it through 22 degrees in a horizontal plane, and at the same time alternately raising and lowering the casing to facilitate penetration. Note the hydraulically operated pads and rails which enable the machine to move forwards, backwards, or sideways. For drilling in sand and silt, this rotary drag bit was used instead of a standard Bonotto bucket. Note the removable cutting bits. The drill bit was designed and built on the project and is capable of drilling in sand and silt at the average rate of 20 feet per hour. The drilled material is removed by means of an airlift. The drill stem consists of 30-foot sections of 6-inch diameter heavy-duty pipe, bolted together with flange connections. 2 1-inch diameter pipes are attached to the drill stem to convey compressed air to a point in the drill stem just above the drill bit. The casing is 36 inches in diameter, rolled from 1/2-inch steel plate, and fitted with 12-inch male and female collars, fitted with aligning lugs and 3-inch diameter holes for connecting buttons. Each 30-foot section is lifted over the drill stem and lowered into position. The collars and connecting buttons were redesigned on the project, as the original design was found to be inadequate due to the high stresses imposed on the casing connections during drilling. The original French casings were 20 feet long, but the redesigned casings were extended to 30 feet to reduce the time required to make connections. The vertical drill frame was extended by 10 feet to accommodate the longer casing sections. Here we see the buttons being inserted. The original buttons were found to be unsatisfactory due to a high incidence of fracture and high replacement cost. A new type of button was therefore designed on the project at a quarter of the cost of the original button, and there were no more failures. After the buttons are inserted, they are secured with spring clips by means of special pliers. The oscillating grip ring seen here, clamped into position, transmits the power from the oscillating mechanism to the casing. When the next section of casing is in position, the hydraulically operated rotary table is lowered and the drill stem is connected to a Kelly bar. The guide collar suspended below the rotary table holds the top of the casing in position. As drilling proceeds, water is introduced into the casing through a 6-inch line at a rate of approximately 800 gallons a minute. The drilled material is forced from the boring by a combined flow of air and water, and eventually discharged through the Kelly bar, swivel head, and flexible discharge hose into the river. The volume of air and the speed of rotation is varied according to the density of material encountered, and some excess water overflows from the top of the casing. The rotary drill is operated by a variable speed hydraulic drive, which is in turn powered by a pump from the main engine. The rotary table, drill stem, and casing oscillating mechanism have independent controls. This arrangement enables the position of the drill bit to be altered in relation to the cutting edge on the casing. The casing, therefore, may be penetrating in advance of the drill bit or vice versa, depending on the nature of the soil being drilled. Actual drilling speeds of up to 60 feet per hour can be achieved with this equipment. If, however, the time taken to make new connections to the drill stem and outer casing is taken into consideration, the productive drill rate in soft material is reduced to 20 feet per hour, or 1/3 of the actual drill rate. Here we see the waste material being dumped into the river. Once the drill has penetrated the sand and silt and reached a layer of clay or hard material, other means of excavation must be used. The drill is therefore withdrawn and each section of drill stem unbolted. The Bonotto machine with the drill rig then moves on to a fresh location and a second Bonotto machine is moved into position. This second machine is fitted with a cable-operated clamshell bucket capable of excavating 2.5 cubic feet of clay per load. Excavation in clay was achieved at the rate of 10 to 12 feet per hour, and in the hard glacial till at the rate of 6 inches to 3 feet per hour. When large boulders are encountered in the excavation, this rock-breaking drop hammer is inserted into the casing. The hammer used in this operation weighed 5 tons. The following sequence shows the clamshell bucket in actual operation. The loaded bucket is withdrawn and automatically tilted to enable its contents to be discharged down a chute into a skip. The skip is then lifted by crane and discharged into a waste area. The rate of excavation is considerably lower than that of the rotary drill, which is a continuous operation, whereas the clamshell bucket has to be raised and lowered through a depth of up to 200 feet from the surface. This brush cleaning plant is the first stage in the preparation of sections of pipe pile, which will eventually be inserted into the pre-bored holes and will support the weight of the finished bridge. The outer surface of the pipe is thoroughly cleaned by means of these powerful spring-loaded brushes, which revolve around the pipe as it's fed slowly through its entire 40-foot length. Here is the equipment in motion. After the pipe has been brush cleaned, it must be specially treated to resist corrosion from the brackish water with which it will be in continuous contact. In this tarring and wrapping plant, the pipe is first treated with a tar compound and then coated from end to end with strips of fiberglass. A total of 120,000 feet of pipe was processed in this manner and was subject to vigorous inspection before being placed below ground. When the tarred and fiberglass-coated pipe emerges from the plant, it's carefully stacked for drying. The pipe pile imported from England is 24 inches in diameter and 3/8 of an inch in thickness. The bottom section of pipe up to 80 feet in length is 1/2 inch in thickness to withstand the additional stress placed upon it at the greater depth. The bearing pile points were cast locally and are seen here already welded to the bottom section of the pipe. When it becomes necessary to use shorter lengths of pipe or when the ends are irregular, sections are cut with a beveling machine. The pipe pile sections are first welded horizontally to produce 80-foot lengths. Here we see the pile point and first section of pipe pile being lowered into the pre-bored hole. In addition to the Bonotto machines used for drilling and excavation, a Northwest 80D crane fitted with a 100-foot boom was used for handling the 2-ton casing sections. In order to handle these 80-foot lengths of pipe pile, it was necessary to use a Manitowoc 3900 crane fitted with a 140-foot boom. It was originally planned that all pipe pile welding would be done in the vertical position in standard 40-foot lengths. It was found, however, that in spite of the necessity of having to use an additional crane, a considerable saving of time and money could be effected by welding in 80-foot lengths. After each section has been lowered to a convenient depth, a welding clamp is fitted round the pipe at the section joint. The welding operation is undertaken under close engineering scrutiny, as no chance can be taken of weld failure after the pile is in its final position. A new 80-foot section is now hoisted and carefully lowered into position. Then, finally, the welding clamp is locked securely into place. Welding then commences between the sections of the welding clamp. After the welding operation, the clamp is removed. Following removal of the clamp, the weld is completed and the pipe pile lowered to its required depth. The lower 10 feet of pile is then filled with dry mixed concrete. Once it's full, the pile is hammered internally by means of an 8-ton drop hammer. To prevent flotation of the pile after placement, large diameter lead-filled donuts are hung on the top of the pile. Pile hammering continues until penetration is less than 1/2 inch per 10 blows. To achieve this penetration, the hammer is dropped approximately 2 feet to produce 32,000 foot-pounds of energy. When the design bearing has been attained, the hammer is withdrawn and the rest of the pile is filled with concrete. The concrete mixing plant was required to provide approximately 20 cubic yards of concrete for each pile, or a total of 12,000 cubic yards. The concrete is fed by conveyor and discharged into buckets having a capacity of 1.5 cubic yards. The buckets are then hoisted into position at the top of the pile, the rate of discharge being controlled manually by means of a rope attached to the release mechanism. While this operation is in progress, drilling and excavation continues elsewhere in the pier at predetermined locations which are carefully planned to ensure that all items of equipment are operated at peak capacity. When many large machines are required to be operating at the same time in a confined area, economy of movement and rapid handling is of the utmost importance. Here the hopper is being removed from the pile after completion of the concrete operation. The next stage in the operation is the preparation of clay grout, seen here in the mixing plant, which was designed to use a 12 cubic yard agitator and 2 paddle-type mixers built on the project. The batch plant includes a semi-automatic weigh skip and extra bins to handle clay. The grout itself is a mixture of clay and cement and is used to prevent overloading by friction due to settlement of the soil surrounding the pipe pile. The grout is introduced into the excavation between the pile and the outer casing, the rate of flow being controlled by this system of valves. The grout is pumped into the excavation by means of a high-pressure double-piston pump, and in addition to preventing overloading by friction, provides additional lubrication during withdrawal of the outer casing. The pipe carrying the grout is coupled in sections, seen here being removed after completion of the grouting operation. All that now remains to be done is to withdraw the outer drill casing, leaving a concrete-filled pile surrounded by grout. The Bonotto extractor withdraws the outer casing with the same oscillating motion that occurs during excavation. The standard Bonotto machine can also be used for extraction, although if this is done, much valuable drill time is lost. The use of an independent extractor, therefore, permits the more expensive standard machine to be used continuously for excavation. On this project, it was calculated that by using a separate Perini-built extractor, the total duration of the job was reduced by more than 100 days. As the casing is extracted and each joint appears above ground level, the buttons are removed and the casing stored for future use. In the final stages of pile installation late in 1961, a maximum of 18 piles were installed in 1 week. Here is a view of the South Shore showing the superstructure under construction on the 4 land piers. When completed, the columns will support the approach span to the bridge. This pier is located on the south bank of the river and was the last to be constructed. Moving out into the Fraser River, looking towards the North Shore, the foreground shows the location of the 2 river piers with their working platforms and connecting trestle. In the background can be seen the superstructure for the northern approach, which will carry the highway to the river bank. On the South Shore, concrete buckets are loaded from ready-mix trucks and transported to the river piers by barge. These piers are enclosed by cofferdams constructed of interlocking steel sheet piling and which protect the work under construction from the tidal waters of the Fraser River. The underwater concreting of these piers was undertaken by the intrusion method without dewatering and without the necessity of using the normal cross-bracing of the cofferdams. This close-up of the cofferdam shows concrete for the pile caps being unloaded from the barge. And here is the interior of the cofferdam showing the pier in readiness for the concrete capping. When completed, this multi-million-dollar project will forge one of the final links in the chain of road and bridge projects across Canada, providing a transcontinental highway from coast to coast. The mighty Trans-Canada Highway will bear tribute to the engineering vision and ingenuity, which by improved transportation and communication facilities will provide greater wealth and opportunity for future generations to come.